All right, I'm back in business now. All right, so our plan for today is to finish up chapter 2 and get started on chapter 4. And chapter 4 should hopefully the material that is new to you, maybe less review. So the last few things in chapter 2 are talking about, in general, some properties of water. So just a few terms that we need to go over is the difference between hydrophobic, hydrophilic, and amphiphilic. So if we have a hydrophobic system, we have a system where the water chooses to stay with itself and the non-polar molecules stick with themselves. And this is going to affect our entropy of our system. So when we think about what's happening to the water, if the water is choosing to all aggregate with itself, is the water becoming more or less ordered? More ordered. So is that increasing or decreasing our entropy? Decreasing our entropy. The reason we care about hydrophobic effects is that it's going to affect how our proteins fold. So if you have an amino acid that is hydrophobic, those amino acids are going to choose to self-assemble with each other, and it's going to push the water to hang out with itself. And so this is an effect that strongly affects protein folding. That's a G, not a Y. There we go. All right, we have hydrophilic effects where water is polar, right? And that polar water will be able to dissolve ionic and other polar substances. So then these substances become what we call solvated, which means that the individual molecule, whatever it is, we'll say Na+, now has a big old bunch of water surrounding it. That help transport it from one place to another. So it's like being dissolved in a very specific sense. Then our last category is amphiphilic. It is where water can act as both a non-polar and a polar substance. So amphiphilic molecules, let's see how that works. So polar and nonpolar, we'll call it Ns. And these are compounds that can form micelles or bicelles, and these are our fatty acids typically. And so here we have an example of a fatty acid, palmitate, which has a long chain of carbons, and then our carboxylic acid group. So we have a long saturated chain attached to a carboxylic acid group. So then we have this side, which is our polar end. And we got this end, which is our nonpolar. And so in a micelle or a bicelle, depending on how many layers there are, I'm just going to draw a circle and then a long line as my fatty acid, where this is the polar, this is the nonpolar. These are going to choose to aggregate. Which end is going to want to associate with the water, my polar end or my nonpolar end? Polar end. So they're going to start to associate like this. Where all my polars are on the outside being surrounded by water. And all my nonpolars are on the inside associating with each other. This is a micelle, where it's just kind of a sphere, a single sphere. If it was going to be a bicell, it actually is going to look more like this. So that structure is about the same. But then it has another group on the inside. So this is more like your cell, where there's an outer fatty acid and an inner fatty acid layer. And the heads are all on the outside and on the inside. And then we got all these tails on the inside. So it looks like that.
So are the tails on the inner one
Yep.
facing outward, or they're still facing in?
They're facing in. So all the tails are on this part. Those are all tails.
Okay.
And the edges are all the heads. Makes sense? Okay, question about any one of those three terms? Okay. Let's talk about 4 things that are fascinating about water.
And the second one that you drew was a bicell?
Yes, that was a bicell. All right, so 4 things that are really interesting about water. One, we've covered a lot, that's polar. That it's able with both hydrogen bonds, ionic interactions, dipole-dipole. It's able to do all of those things. Water also has a high heat of vaporization. So what state of matter am I going from if I'm vaporizing something? Liquid gas. So, right, water's my liquid and steam would be my gas. Why do you think it's handy that it takes a lot of energy to boil water? Thinking of yourself as a human being outside in Georgia where it's hot. Your body's like a lot of water, so it's a good thing that your body doesn't spontaneously boil when it gets too hot. It takes a lot of energy to boil that water. So when I say high heat of vaporization, it takes a lot of energy to boil it, which is good. It means your body stays at a liquid state most of the time. All right, high heat capacity. Heat capacity, back from thermo, when you're doing your coffee cup calorimeters, you're measuring the heat capacity of water as one of the things. Anyway, heat capacity is how much energy is required to heat 1 milliliter of water 1 degree Celsius. That sounds vaguely familiar. So how much energy it takes to heat that little bit of water. This is super useful for your body because it means that you are able to maintain a fairly regular body temperature. Right? So if it takes, how much energy is required to heat 1 degree or 1 mil of water just 1 degree, And if it takes a lot of energy to do that, it means in general, your body is able to maintain a constant temperature. And then we have a high melting boiling point. This is good, not just thinking about yourself, but just in general, the entire surface of the earth. The fact that water has a high melting and a high boiling point means that water maintains its liquid state more than it should. More than what you would predict if you didn't know anything about water. Oop. Hold on, I lost my train of thought. It means that water maintains its liquid state more than, there we go. Forgot half my sentence. Means that water maintains its liquid state more than is predicted based on similar molecules. So if you're looking at other things like something like that, or, oh, my periodic table tipped over. If you were going to compare things like that to water, water is very, very different in the fact that it takes a lot of energy to heat it, to vaporize it, to boil it, melt it, more than what you would predict if you were just going down the periodic table and looking at similar molecules. Okay. Last two things about water's chemical properties. And we've already talked quite a bit about the hydrophobic effect. But water is a solvent. Water is a great solvent because it has the ability to form hydrogen bonds. This comes from the fact that it is just this combination of molecules. It's just an oxygen and hydrogen, both of which are able to form hydrogen bonds. And so together they can form a lot of hydrogen bonds. Which means it makes a great solvent for biomolecules. That are often ionic or polar. And the hydrophobic effect we just talked about, that nonpolar substances don't dissolve in it, but phase separate to make structures like micelles and bicelles. Which is good because bicelles are pretty much what cells are. They're just a bicell, bilayer of lipids. All right, any questions on all the kinds of fascinating facts about water? Okay, good, great. Let's talk then just a little bit about acids, bases, and buffers. Who brought a calculator with them today? I'd go ahead and fish that out. We're going to work our way through a few just review problems that you probably have seen before. right, so water ionization. So if I have water in its liquid form, what are the two compounds that water can form in equilibrium with itself? One's hydronium, and then hydroxide. So if I was to write the equilibrium equation for this, I have it right here. So the equilibrium equation for that reaction is here, this KEQ equals products over reactants. Why did I square that guy? Because there's two waters. Perfect, that comes from that. What can I do to this equation to simplify it? Okay, when I'm thinking about an equilibrium equation, what things do I not typically include? Liquids, solids, gases, and any other pure substance. So what can I do to this to simplify it? Yep. That's just going to be equal to 1. Why can I not make that 0? Yeah, something over 0 makes calculators angry, which then means you did it wrong. So it should definitely not be 0. So I'm going to rewrite that. Okay, this happens to be a special equilibrium constant. It's going to be called Kw, because it's the equilibrium constant of water. And so it just has its own little W at the bottom, which means water, which happens to equal 1 times 10 to the negative 14th at 25 degrees Celsius. Why does it matter what temperature for this? Partly that, and so it partly also tells me what ratio I have of these two. So if we think back a little bit earlier, right, delta G equals, and we related it to the equilibrium constant, but it had a temperature effect. So it tells me about spontaneity, tells me about what ratio I have of the two of them. So I think in your chapter 2 homework, there's at least one question where I want you to calculate Kw at a temperature that's not 25. But we'll get there. All right, KWs are important to talk about the pH of a solution. So just quick review, we'll look at acid, base, neutral. All right, what pHs are considered the acidic ones? Below 7. Mm-hmm. What pHs are considered the acidic ones? Above 7. What's typically our upper limit of a pH? 14. Mm-hmm. So really this is saying 0 to 7. This is 7 to 14. And then I'm going to assume everybody by process of elimination figured out that 7 is neutral. So I'm going to use this Kw to figure out why we have each of these pHs. So let's talk about neutral pH. At neutral pH, it's pH 7. But what does that tell me about the concentrations of each of these? They are equal. So if they are equal to each other, they're equal to that, which equals 1 times 10 to the negative 14th, which means they both equal 1 times 10 to the negative 7. Okay, so I didn't do any fancy math on that, right? Everybody got that? so then let's take a look at, I guess I will write on the back of this because I'm going to write real big. Okay, for an acid, we just said that pH is going to be less than 7. So of those two species, which one is the greater, the predominant species in the solution? This one, right? So if that's true, what does that tell me about the concentration of hydroniums? Will it be greater than 10 times 10 to the negative 7th or less than 10 times 10 to the negative 7th? Greater. And we'll do the same argument for a base. All right, in this case, which one is the predominant species in water? Hydroxide is greater.
What is the M?
Molar. Sorry. My moles per liter. Everybody should remember that equation, right? pH equals negative log of the hydronium concentration. Should be at least kind of familiar. This is where we're going to use our calculators. So go ahead and plug in, let's say I have a hydronium concentration of 5 times 10 to the negative 4th. What is that pH for that solution? I see it off the top of my head, so I have no idea what the actual answer is. Everybody, something like that, 3.3-ish, depending on how you do some entering. Does that pH match up with what you know about acid pHs? Good, excellent. You mathematically confirmed what you already knew. Good. All right, what is the issue here with my pH equation? Right, it's not in the right form. How would I go about, let's say I had, let's say that's the actual hydronium concentration. There are two different ways you could go about solving this. What would be one way of figuring that out? You can use the fact that Kw equals 1 times 10 to the negative 14th, which equals this times that. The other way would be use our POH, but how would I get from POH to pH? How are they related? They should equal 14. So go ahead and either way you want to do it. This is my hydronium concentration. You can either do it way 1, way 2. They're a similar amount of work. I messed that up. I'm kidding. That can't be right. That's not bigger than that. That has to be to the 5th. So I was looking at it, I was like, why is 9 bigger than 7? It's not. That should be to the negative 5th. Continue solving. Sorry, typo. Makes more sense. If we use the actual right number, 4 times 10 to the negative 5th,
What did you have written down before?
to the negative 9th. And that doesn't work because to the negative 9th is not greater than to the negative 7th.
So what did you do with that number?
Sure. All right, so if I used this method, but you could use either one. I said that KW equals 1 times 10 to the negative 14th, which equals 4 times 10 to the negative 5th times x. So I do that divided by that. So x equals 2.5 times 10 to the negative 10th.
So how did you get the 4 times 10 to the negative 10th number?
I just made it up off the top of my head.
Oh.
I just came up with a concentration of OH that was greater than that one. Kind of freewheeling today. Or you could have done it this way, where you plug this into there, solve for POH, and then subtract that number from 14. They should come out about the same. Still some questions? All right, I'll let everybody finish thinking through that. And then let's talk some more specifically about acids and bases and KAs and PKAs. Everybody remember those from organic or Gen Chem? I know you do a lot of stuff with pKa in there. Okay, acid bases and pH.
So just read it. What was the final answer for the
9.6.
that was the pH?
Yeah. All right, acids. What is the major characteristic of an acid? What's the one thing acids are known to do? They give away hydrogens, give away protons, right? They are proton donors. So if I'm going to write my hypothetical reaction of an acid, where I put in acid HA into some water. What happened to the water? It gained a proton. What happened to the acid? Lost a proton. Okay? So if this one is the acid, how is the water acting in this case? Acting as a base. Over on this side, which one of these two is acting as the acid? Which one of these can give away a proton? Hydronium or A-? Okay. Yep. All right, so for acid-base chemistry, there's always an acid base on the left, an acid base on the right. What relationship do these two have? They are conjugates of each other. And the same for this, yeah. So since I've now written the equilibrium equation, I can now write an equilibrium equation for this reaction, right? I got my products over my reactants. What's the simplifying step we have to do in this one also? Get rid of that water, make that 1. So this is my acid that I started with. That's an acid. This is a base. On my scale of pKa's, is it possible to have a pKa of 0? Or a Ka, is it possible to have a Ka of 0? No, right? Because you have to start off with something. So Ka's don't go down to the 0 scale. There's no 0, okay? So Ka's are related to the number 1, right? Equilibrium constants are related to 1. Acid constants will be related to 1. So Ka's closer to 1. If they are closer to 1, what does that mean about this ratio of top to bottom? If it's actually 1, if Ka was 1, what would the ratio of top to bottom be? It'd be at equilibrium, that they'd be equal, top and bottom will be equal to each other. So Ka, so they're closer to 1, means HA is a strong acid. Why would that be a true statement? If HA is a strong acid, if this is a strong acid, does it choose to go mostly to products, or does it choose to mostly stay as reactants? Right, strong acids want to go this way. So it's going to make a lot of our product. So the closer to 1 means the stronger the acid, the more products it is made. They'll always be fairly small compared to your starting molarity, which is where it's a little funky. But the numerator will be large. Yeah. What about our strongest acids? What about our hydrochlorics, sulfurics? Do they even have a Ka? Fun fact, they don't. They don't have a Ka. Not measurable. As soon as you put HCl into water, it completely dissociates. And so if it completely dissociates this concentration 0, then what happens to your Ka? Angry again. So strong acids don't have a Ka. Another fun fact you can share with your friends, your roommates, bring up in conversation. Unless your roommate and or friends are just all in here, in which case they already know it. All right, what about bases? What is the job of a base? Proton acceptors. So let's say I have my big old base over here. What is one of the products that's going to happen when I put my base into water? I'm going to make some hydroxide. If that happens, what's my other thing? Where does that proton go? Yep. What's missing from this side of the equation? What have I done wrong about my BH? It needs to be plus. Why did I know it had to be plus? Has to go from neutral to charged, plus my overall reaction wasn't balanced, right? I had no charge over here. I had a minus. You can't just have a minus floating by itself. It has to have a buddy. It has to be a plus. Good. All right, so then let's say I want to write the equilibrium equation for this reaction. What goes on my numerator? The top. What goes on the top? OH minus, yeah. And then my BH plus. What goes on the bottom? Just B. Using the super clever lingo where this A means acid, what should I call this kind of equilibrium constant? KB. These aren't used as often. Your textbook will only have KAs, but it may ask you how to relate KA and KB, and we'll get to that. So any questions on this slide? Feel pretty confident so far in that review? I promise next week we'll get to some new material. Just want to make sure we're all on the same page about this. All right, pKa, in a similar vein to pH, pKa, where that P means negative log of the thing I'm going to say next. So pKa is the log of Ka. All acids are classified by the Ka, like we just said. Weak acids have Kas less than 1, right? There's no Ka equal to 0. So you're either less than 1 or greater than 1. And this, you can check back on the previous slide, but it comes from the fact that Ka is just that same equation. If you just wrote this, you don't have to write it again. Right, so weak acids have a Ka less than 1 because this has not dissociated completely. Strong acids have this completely dissociated, so it has this big, big numerator over the denominator. So let's do some practice problems. Let's say I have acetic acid. Let's see if I can. The Ka of that is 1.74 times 10 to the negative fifth. What is the pKa of that acid? Go ahead and just plug it in there. What did we get, ish? Yep, I'd say 4.76, depending on how you end up rounding, 0.75, 76. All right, let's do 2 more. So for citric acid, I give you the Ka, find the pKa. For lactic acid, I've given you the pKa. Find the Ka. All right, any thoughts on my citric acid pKa? I heard 6.49. Good. All right, what about the Ka of lactic acid? What number does it start with? A, okay. All right, is anyone confused about how to back this up? Okay. So pKa, what I'm going to do is I'm going to say 3.08 equals negative log Ka. What on your calculator, look how clever that is. What on your calculator is the opposite of the log button? 10 to the, right? 10 to the. So I'm going to do 10 to the 3.08 equals 10 negative log Ka. So if I do that, 10, I lost my train of thought. You get something, oh, I'm sorry, I messed it up. That log, that negative should be over here. So the first step should be this. So the first thing you should do is switch that negative sign over. So now it's negative 3.08 log of Ka, and then do 10 to the negative 3.08. And that should 8.3 to the negative fourth. Everybody get that answer? Good, good, good. Awesome. Okay. So then I can plug that in there. So looking at these Kas, these three right here, which one of those acids is the strongest based on their Ka? Lactic acid. Lactic acid is the strongest out of these three. It's not strong, but it's the strongest. So either it has the smallest pKa or it has a Ka closest to 1, both of which are true statements. All right, does anyone recognize this equation? My favoriteest equation ever? Hint, the HH equation. It's my buddy Henderson Hasselbalch equation. And we're going to talk about buffers. All right, keep the screaming down. We'll cheer about it in a minute. Well, let's talk about buffers. All right, so this is our conjugate acid-base combination that over a small pH range resists change in pH. All right, so let's go back to my just water equation. All right, I just have plain old water interacting with an acid to make a conjugate base and a hydronium ion. If I wanted to write the Ka equation for this, what would go on the top? Some hydroniums. And that on the bottom. Right, so far so good. Pretty much if you flip back 2 slides, we already wrote this once, so super review, like 10 minutes ago review. All right, I would like to rearrange this so that this hydronium is by itself. What's the first step I need to do to get this hydronium bracketed thing by itself? Okay. Okay, what's step 2 to getting the hydronium bracket by itself? Okay, divided by A minus. What if I wanted to talk about pH instead of hydroniums? What do I do to this brackety hydronium to turn it into a pH? What does the stand for in math? Negative log. So we're going to take the negative log of both sides, which I'm going to go ahead and just like skip ahead a step. Just in the sake of time, I'll do this. Using our log rules, where if it's a division, it's really subtraction in log terms, which I'm sure everybody knows. If not, you can come by my office and we'll talk about it, because I do love negative logs. So I took the negative log of both sides, which because this is a division, is now a subtraction. What's the negative log of Ka? What's another word for that? pKa. Look what you just made. The Henderson-Hasselbalch equation. Look at that, in just 5 easy steps. you got from an equation to the Henderson-Hasselbalch equation. Okay, this is going to be our use with buffers equation. It relates the pKa to the pH of the solution. It relates the concentration ratio of the conjugate acid and base. That ratio tells us about the pH, right? It's super useful because you only have to know a few pieces of information to find the other ones. All right, we will stop there. That's pretty much the end of chapter 2. So when I see you on Wednesday, we will talk about chapter 4 and amino acids and everything fascinating about amino acids.